this topic. Chapter 2. So can you see? Lecture notes well, huh? Okay. So please pay attention. Today, actually, I will use this definition. F of C, C is a subset of A, is a set of all values of the function f such that x belong to the C. Okay, which is this one is a subset of B, and this set composed of the image and the f of all the elements. Actually, A is the domain of f. Huh? So, and f minus 1, we need this definition as well. Remember, please, it is the all values of x from A such that f of x belong to the E. So this definition is used today. Okay. By the way, I want to tell you, I constructed or actually prepared quiz 2. Okay. Quiz 2, pay attention. It is on the topic of this area up to here, uniqueness. Okay. Using uniqueness, this is one topic. Okay. Then okay, please pay attention, huh? And look, the first example, first question I choose as example. No proof. Just you need to solve the problem. Okay, as an example. For the second question, yes, I have the proof as well. So please, what does it mean injectivity? What does it mean bijectivity? And how to find, for example, the f of A or f minus 1 B, how to find in the example. Function is given. So how to find two exercise, okay? So from this topic, I choose one example. Then second example, after knowing the injectivity and subjectivity and bijectivity, so I choose one questions around this part. Okay, so how to prove injectivity and bijectivity. Okay, so using some given functions. Okay, so that's why please up to here I choose two questions actually. The equivalent set I didn't add. So the only part one. So two questions. Okay, so please properly read and learn. Do exercise. Okay, so that is my first advice, please. So up to here, I have chosen two questions. Okay, injectivity, surjectivity, bijectivity. Please properly learn. Now we started equivalent sets. Huh? So please, in the equivalent sets, pay attention. So it's actually equivalent set is not equal sets. Equivalent sets. So definition, please memorize. So two sets A and B are equivalent if there is a bijection function, not only injective, bijective function. But in order to find the bijective function, yes, we have to find the injective function. Injective means one-to-one function. And for the injectivity, you should use this definition. Please pay attention. Here, I will show you one more time. For the injectivity, you need to find this, the f of x1 f of x2, it implies x1 equal to x2, then this function is for any x1, x2 from the domain of f. The f is not part of the, it is a whole domain of f. So if this inequality implies this function is called injective function. Okay, and for the surjective, actually this one also can use, but mostly this. You see, f of a, because for the f of a, how to find the image of a in the set B. We know that by definition, we solve f of a. If that f of a is equal to b, which is b is a codomain of f, so then, so you see, this inequality actually helps us to find the surjectivity. If you remember, for example, for these two examples, one is linear function, one is quadratic function. So for the quadratic function, look, the G maps R to R. So domain is for whole R. Then you see here, they just say like this. Actually, if you say f of a, pay attention to show the surjectivity in the example, okay? That one, we really need to do some so I think, okay. So for this example, look, f of x equal to x squared. Injectivity very easy to show, right? So f of x1 equal to f of x2 doesn't imply x1 equals x2. I am showing the surjectivity. For the surjectivity, so here this f maps R to R and domain of R, which is A.
Doctor, we cannot see.
Plus infinity. Big video. Should be video. Okay, here's close it. I mean, go to the stop sharing. I hope, okay, over there should be video. Okay, now they can see me, I think. Huh?
Okay. Ya.
Can you see that?
Lagi belakang.
Okay. Oh, very good. So over there can see, yeah. So please, I'm trying to find the showing the surjectivity. Okay. So the surjectivity says if f of definition f of a equal to b, b is a range of f. If they are equal, then that's the surjective. So now how to find f of a? By definition, it is a function of f of x such that x belong to a. Okay, now x belong to a means, so here I have x like this, x from minus infinity to plus infinity, because a is like this. So x belongs here. From here, I will come to So raising to the square gives us 0 to infinity. 0 to infinity. So this f of x belong to from 0 to infinity, which is not equal to so actually which is not equal to a, yeah? So b actually for the b we found actually is not surjective. I want to show that it is not surjective. It is not equal to b. So what about b? So for the b, and this is b, correct? This is b. This is b, but not equal to a. Actually, domain and the codomain should be equal. Here, codomain is from 0 to infinity. A is from minus infinity to plus infinity. Okay? So, actually, here, codomain B is actually here from 0 to infinity. See, RF is from 0 to infinity. But it is after solving this equation, you see here important. From here, I can get the function interval of the function because definition says f of a is a set of all f of x such that x belongs to the a. Okay? So I hope from this picture you can see how to prove this surjectivity. So surjective is actually onto. Okay. In other words, over there they say that for the surjectivity, for every x, actually today I have another. You see this equation for every x from domain A should correspond one value of y. One value of y for every x. Onto means for every x should have one image. In other words, satisfying this equation. Okay, so later on I will show you. So okay, next I will just this one, you know, for the preparation of the exam as well, and the proper understanding of injectivity and surjectivity. So now definition, the second definition says for the equivalent. List says so these two sets are equivalent if there is a bijective function mapping A to B, B to A. Okay, bijective function. So this theorem is already proven. So A is equivalent to A. If A is equivalent to B, then B equivalent to A. So third one, this is symmetric, reflexivity, and transitivity. So for the first one, we have bijective function. See this f of x equal to x is bijective function. Is 1 to 1 and on 2. So A is equivalent to A. For the B, there is a bijection function. You see, if A and B, then there is a bijection function. If bijection f is a bijection function, then inverse is also bijective. Based on what? F is bijective, then f minus 1 is also bijective. So it comes from here. You know, it comes from here. There is a okay. Look, if f is injective, then okay, this one the mapping actually inverse from. So where if f is injective, then f minus 1 is injective. Okay. You see, if function f is injective, then f minus 1 mapping. You see, mapping from Rf to A is also injective. So the second one, for any function f, the inverse from B to A is a function if and only if f is bijective. Bijective is injective plus surjective, right? Surjective. So this corollary 1, 1 and corollary 1, 2 gives equivalence of A and B. Okay, so that one we should understand properly. So now, okay, you see, proof I think is proper because if A is equivalent, you see, when we say A set A is equivalent B, it means there is a bijective function between them. If f is a bijective function, f minus 1 is also bijective, inverse function. So that's why here, for this case, of course, we have composition function. So this one is an example for the composition function, okay? Because here also they say composing. You see, A equivalent B, B equivalent C means F mapping A to the B, G mapping B to the C. Then the composite function mapping from A to C is also bijective. Then we should have A. This is the proof of that theorem. Second one, now F is finite if it is empty set, or there is a natural number n such that A is equivalent to the natural number set. Natural number set. Actually, 1, 2, 3, and n is a finite number of the set. So, in other words, this definition says if we are able to count the element of A, right, by finite number, then it is these two sets are equal, are equivalent. So here equivalent. So the finite, actually A is finite. A is finite if there is an equivalentness of set A and the set of 1, 2, 3, and n set. So it means that element of A can be counted. So that's why here they use the cardinality. So cardinality of set A means the number of elements of A. Okay, number of elements. But here pay attention. For here it is already given example or not. But look here, just a little explanation. So for example, if set A is given like this, what about cardinal number of A? Okay. Now just I will give like this. Number of the elements of A is given. For example, 1, 2, 3. 1, 2, 3. Okay. So this set has 3 elements. So another B has 5 elements. So 1, 1, 2, 2. 5 elements are here. And 3. But in terms of cardinal number of A, equal to B. So number of elements actually is counted as non-equal elements. Understand? This is one of the definition of cardinality. Okay? Cardinality. Cardinal of A, cardinal of B are the same. Even they have, you see, this one looks like 5 elements, this one looks like 3 elements. So this repeating number actually skipping in the counting of cardinality. So please pay attention. If A is an empty set, then this cardinality is 0. Okay, meaning that cardinality of A. If A is 1, 2, 3, and n, see equivalent. Then A has exactly n elements. Cardinality is equal to n. Okay? You see A set is not exactly equal 1, 2, 3, n, but equivalent. For the equivalence, we should have the bijective functions. Okay, so this one already we previously discussed well, but just I am reminding you for finite set A and B, it follows that transitivity, if and only if, you see, if cardinal number of A equal to cardinal number of B, so then we say that A is equivalent to B as well. You see, cardinality implies equivalence of the sets. Okay, please be another careful. But if A is a subset of B, then cardinality of A is also less than, you see, proper. Proper means that there is element B which is not in here. So B is the largest set. A is a subset. So in that case, cardinality is also strictly toward the strict inequality. Strict inequality. Are not equivalent. In that case, you see, if cardinality not equal, then this one is also not equal. Such the relation partition finite sets into the equivalent sets. So these sets in any one class have the same number of elements. Okay. Now second results. Look, we have already discussed it. I don't want to stop here. We have N1 odd integer numbers and even integer numbers. Actually, in terms of numbers, they are different. This is 1, 3, 5, and so on. This is 2, 4, 6, and so on. Now, how we say what and how we prove that these two sets are equivalent sets? So, if for the equivalentness, so we have to find bijection function such that N1 maps to the N2. We need to find. For example, for this case, very easy. F of n, you see, this f from n. Taking n, if we add any odd numbers here, we are taking, adding 1, we will get the even numbers, right? So f of n, this function, is bijective. So it is 1 to 1 and 1 to 1 to. So we are able to find bijective function. You see, that one implies n1 is equivalent to n2. Okay, now slowly we move. The bijection function from n to n2. Now look, n is a natural number set. Actually, in terms of cardinality, can I say the cardinal number of integer n and even integer are the same? How much the cardinality of even number? You see here. So G, you see n, here n1, n2, here n to n2, also equivalent. N to n1 is also equivalent. But how to find again on the whiteboard, because this shows a lot of important points for proving of the equivalentness. Okay, look, I am taking as a n natural number set 1, 2, 3, and so on. So as a b, I am taking n2. As I say, n2 sub 2. So which is 2, 4, and so on. How to calculate the cardinal number of A? Can you count? Cardinal number of n. How many? Please count properly. 1, 2, 3, 4. I'm counting. So how many cardinal number? Cardinal number is a number of the sets. So how many elements? Infinite. Correct. So this one is infinite. What about cardinal number of B? Also infinite. You see, even it looks like less than that, but in terms of cardinality, they are infinity. So it means A equal to B. In terms of cardinality, N equal to B. Okay? But currently, this one not implies that they are equivalent. For the equivalentness, we have to find bijection function from N to N. Okay? Now, it is already found G function. If G function is given as 2n, so this function maps, you see, n derives from capital N, natural number. This n, it maps to n2. N2. And, okay, can I show this function, Gn, is a injective and surjective to be bijective? Okay? I will show. I will take two numbers. So this is 2n, 1 equal to n2. So if I divide n1 is equal to n2, you see, this implies this injective. This injective. Now, how to find the surjectivity? Show the surjectivity. To show the surjectivity, we should have G of A, G of A, here A, please pay attention. A is what? A is a domain of G. Domain of G, here we can see, is domain of G is actually N. I can see domain of G is N. 1, 2, 3, N, 3, N. See here, it is not interval. This is number. Okay, now I have to find G of A. If G of A equals D, here, this G function actually maps to what? Maps N to N2. Right? And RG is before finding that. So this is A, this is B. B, you see, is all the odd numbers, even numbers are the codomain. A is all the integer numbers. So now this is for this function. Now I am finding G of A, which is G of N, or it is a function of G of N such that N belong to the A. Right? Belong to the A. So now I to find G of A and show that this one equal to B. Look, it's exactly equal to B. Why? Because instead of Gn, if I put all to n such that the n belong to the A, this is exactly set B. This is exactly set B. So you see, G of A equal to B. So it is surjective. So this function is injective and surjective. So it is a bijective. If there is a bijective function, then these two sets are equivalent. So you see, even natural number set is twice, double than the B, but in terms of equivalent, they are equal. Okay? So you see, there is big differences. A equal to B. In the calculus, A equal to B. And we say two sets are equal. If every element of A is an element of B, and every element of B is an element of A. That one is equality. But here we have equivalence. Okay? This is not this. This is totally different. So for the equivalence, we have to find the bijective. If bijective function is possible, then we say these two sets are equivalent. Okay. So from n, we have shown from n to n2. Okay. Can you construct another function? So okay, construct the g function such that n1 is 1, 3, 5, and so on. Then show that this n1 is equivalent. Can you find g of n function such that how to construct gn from here to here? If I say n plus 1, look, n plus 1, okay, I can say g1 is 2, but g2 is 3. Huh? Look, g of 3 is 4. So I don't have 4 here. You see, g of 1, 2, 2 don't, I don't have. G 3 I have. This one I don't. This is wrong. Huh? There 2n plus 1. 2n plus 1. Okay? Actually 2n plus 2n minus 1. Huh? Because when n equal to 1, you see g of 1, I should get all the elements of this. G of 1 is 1. G of 2 is 3, and so on. Now you need to show this is bijective function. Okay? So now for the equivalent set, we need to find bijective function. Okay? That's the main aim of the topic of this. So from Z, now you see from Z to N is also equivalent. Z is twice more than the N. That's it, equivalent. How to find the function? Can you construct another function different than that, but still there is a bijective function? It is constructed there. Okay? Can you find another one? Example 2.2. 2.2. You see, every time here the function is piecewise function, not one function. Here we are able to find one function. Over there we have piecewise function. You see, but this piecewise function we can show that this function is bijective function. How to show bijectivity? Okay, at the moment there is a proof over there, but according to our this scheme, can we show that that function is a bijective function? Okay, so let me identify, okay, and show the proof of this theorem. You see, now we are moving bigger sets. So now next step, we want to show that Z, which is n plus union n minus n union 0. This is the Z. N is a natural number set 1, 2, 3, and so on. How to show that is equivalent n? Equivalent n. Okay, we have to construct function, bijective function, mapping each other from n to z, from z to n. Okay, it is already there. Okay, fn it is equal to 2n if n greater than 0, strictly greater than 0, and minus 2n plus 1 if n less than 0. Okay, now what about this f? mapping. Now this M F mapping N to Z. Am I right? Look, for every N, opposite, Z to N. Z to N. Yeah, opposite. So N Z mapping Z to N. You see, N can be positive, can be negative. On the other hand, when positive 1, 2, 3, we will get all the integer numbers, 2, 4, 6, and so on. So when N is negative. So with this one, look, when N is minus 1, this is 2 plus 1, 3. Actually, here 0 was included here. When N equals to 0, it is 1. When N equal to minus 1, it is minus 1, 3, 5, 7, and so on. All odd numbers comes from here. All even numbers comes from here. So you see, so this, because here N derives from Z. That f of N maps to Z into N natural number. You see, resulting one gives a now how to show that this one is a bijective function. So first we have to show this function is bijective. To be showing the bijectivity, I say let N is positive, strictly positive. If strictly positive, then f of N is equal to 2N. And just now in the above, we have shown this function is bijective function. Second case, let N is less than or equal to 0. In that case, f of N minus 2N plus 1. Now we need to show this function. Previously, 2N plus 1. Now here, minus 2N plus 1. Different than the previous function. We need to show this one. This function is also bijective. First, injectivity. F of N1 equal to F of N2, which is minus 2N1 plus 1 equal to minus 2N2 plus 1 gives N1 equal to N2. It is injective. Okay, now f of A should be equal to B. A is the domain. Where is the domain of this function? Look, domain from here I can say domain is Z. Domain is Z. So now I want to find domain, the image of the domain. Okay? Image of the domain, by the definition, it is the function of f of N such that N belong to B. B is belong to the A. Belong to the A. This is the definition of f of A. A is Z. Okay. For the second case, if N is minus 2N plus 1. Okay. First N belong to A. Okay. If N belong to the A is Z. So, okay. This one, look. If N belong to the A is Z. n takes the negative value here under this condition. Under this condition, this set gives 1, 3, 5, and so on, which is n1. And this one, can I say it is equal to the b? What about b? B is n. Here, look, this one b. This is the b, natural number. So f of a should be equal to b. But can I say this is not b yet? No. Actually, I should consider all. Okay, I'm wrong here, because under this condition, look, under this condition I will get this. Under that condition I will get, yeah. So here, you know, we cannot solve the equality, but we have to. So now look. So all a n, positive, negative. For the positivity, when n is positive, I get, here when n greater than 0, I will get this f of n, 2, 4, 6, and so on. When n is negative, I get 1, 3, 5, and so on, which is n. You see, f of a equal to n. N is b. This is b. So I got surjectivity, injectivity proof, surjectivity proof, proven. So it is bijective. So this function is bijective. You see, it is not shown in the proper way like this. So now you, I think, understand how to approach. No, you see, for the second case, I am proving it under this condition. Under this condition, this function implies argument equality. Look, under this condition, Fn is minus 2n plus 1. I just use this function. Yeah, for this case, yes, for this case, you can prove the same thing if n1 in if n equal to n1. Yes, because 2n1 equal to n. Yes, yeah, you know, in order to prove, we have to categorize. You see, if not categorize, how you compute it? You see, under this condition, I got this function. In the above, we have proven this function is a bijection function. So under this condition, I have proved that this one is a bijective function, injective function. You see, each cases I consider separately. Okay. Now this function is bijective. This function is bijective. So if both functions are bijective, n must be bijective. For the bijectivity, the second case, you see, this one little bit different actually. So I have to, if A is considered as domain, so I have to find the f of A under this condition. You see, when n greater than 0, I get all even number. Under this condition, I'm getting all even together, I'm getting the n. You see? Together, I'm getting the n. So the surjectivity is counted together. Okay? Is counted together, not separate. Understand that? So that's the proper proof of the example. This is actually example. So now what we have to show the surjectivity, you see, say choose M from M1 plus M2 and if M1, M belong to the M1. There is an analytic function. Not very clear picture. I think here, I think everything is clear now. Okay? So that is a way of proof. In the exam, actually, I leave it this one for the final exam. So in the final exam, if I give the function to show the equivalentness, first of all, you have to construct. Think how to construct function from A to B, mapping A to B. If you are able to construct a function and show that that function is a bijective function, then you will say, oh, this function are these two sets are equivalent sets. Okay. Now, generally, equivalent sets are clear and very properly shown that we have known. Okay. So now, next step, countable sets. Okay. Actually, countable sets is also another interesting topic because this topic shows that later on I will show you the R is not equivalent with finite set. Actually, the definition at the beginning of the definition, we say A is finite. Remember, definition. A is finite if A is equivalent with the set of n numbers. With the set of n numbers. See, we say A is finite, set A is finite if there exists, for example, set B such that so this A is equivalent with this set 1, 2, not infinite, finite number set. This is finite number set. So if A is equivalent to this, A is called finite set. Otherwise, the set A is infinite set. Okay? Not finite, infinite set. Definition of the above is given, right? Now about the countability. So this one is finite set. The A is finite. If there is an n, actually not P, there is an n, such that A is equivalent to this set. Actually, this one, in my case, it is a set B. Okay, now what about countability and uncountability actually? So definition says a non-empty set S is called finite. Set S is called finite if there is a bijection of S with the set of the form. Actually, the definition. Now we are coming to this definition. Previously, what we had, I said the equivalent. This is the countability actually. Sorry, the previous one, the equivalentness. For the equivalent, actually, we have just like this. If there is a bijection function. Okay, sorry. So this one different. For the equivalentness, we need to find bijection function. Okay, bijection function. If we are able to find bijection function, then two sets are equivalent. Okay. Now for the countability, we should use this definition. Sorry. So actually, for the finite set, we use this. You see, pay attention again. As non-empty set S is called finite if there is a bijection function. Again, bijection function of S with the set. So bijection function F from A to B, from A to B, B is this one. Bijection function. if we are able to find bijection function f such that A equivalent B equivalent B. Okay, that is a finite. It's called it finite. For some positive integer m, for some positive integer n. So if no such bijection exists, then the set is called infinite set. So there is finite set, there is infinite set. Second definition: a set A is denumerable. Huh? If A is equivalent to n, enumerable. Okay, and countable if it is either denumerable or finite. So you see the countability actually countable countability divides into two. Please pay attention. Countability if it is either denumerable, or finite, or finite. So please very clear, try to catch the idea. Finite set is a set such that A is equivalent to this set. Is equivalent to this set. Over there, actually, there is for that one, it is called finite if there is a bijection set S of S with the set bijection. Here also we should have bijection function f. For the denumerable, see for the denumerable, f set A actually if there is a bijection function exists such that A is equivalent to the n. N, this definition, n is natural number set. So another word, you see another word. So we have set A and we have set n. So if we able to find the bijective function between them, you see, element of A is not finite. It might be infinite many elements, but there is a equivalence. And for the countability, even if it is a finite, it is say countable. If it is infinitely many elements in the set, it is also, but only pay attention, infinitely many elements, but it can be counted by n. Okay, can be counted by n. Imagine here, if I am taking the set A as a chair of this room, is it finite? Of course, definitely finite. Okay, now I will extend it. So, students of UMT is finite. I will add all the university in Terengganu students, number of the students. Can I say finite? Can I? Okay, I will add, correct, it is finite. Big number, but it's correct. If I take the set A as a student of Malaysian University, private, government, doesn't matter. Can I say it is finite? Right? Okay, I will add Uzbekistan. You see, Malaysian students plus Uzbekistan University students. Can I say it is finite or infinite? Still finite. Okay, in that case, I will add all the world university students. Can I say it is finite? Whole world, not one university, whole world countries university students. Infinite? So you should differentiate between finite and infinite. You see, for the finite, we should have the equivalence of A and B with these numbers. Okay. So you imagine whole university students is also finite, right? We can count it 1, 2, 3, and million, but we can count it. So that one is finite set. You see, finite set actually equivalent with this set. So now I'm going to the infinity set. Okay. So in sinus, it is proven. Number of my hairs. How much? We cannot say it is, for example, billion or 10 billion and so on. We cannot count it. But still I can find, the equivalence between the number of my hair. You see, I'm the one small person. But my hair, number of hairs is uncountable. But it is called still countable. Why? Because I can find the bijection function with infinite sets. You see, n actually is not finite. It is infinite n elements. This one is infinite. You see, these here still can be counted. But of course, you have to find the bijection function between them. Okay? And see, now I will take just very small interval. Just as a, I will take 0, 1, the small, the finite interval. This one finite interval. But element of this interval is uncountable. It means we cannot find bijective function between this interval and this n. Cannot. But interesting point, if I take A as a set of x A over B, such that x belong to the 0, 1. Rational number, okay? I'm x belongs to 0, 1. I am taking, see, all the sets of 0, 1, which is, okay, I think more properly if I write, it is the element of x from R, from Q, such that x belongs from 0 to 1. Look, if I'm taking only the rational number in this small interval, this one, I can say it is equivalent to the n. But finding such kind of function f is a very problematic, but it's proven in the mathematics. Okay, over there also we will try to understand these situations. So, finite set is equivalent with this. Infinite set is not equivalent with that. But now there is a countability. Countability if is countable if it is denumerable. Denumerable means set A is equivalent with the n. Denumerable. So countability is equal to finite and denumerable. So it means this is finite set for related to that and to that. Okay, so now we go to through this lecture and try to understand why this set over there they show this set is not only countable, is not equivalent with the n. And then I say q is belong to the q, it is countable. Okay, here small example. If I take b, just for your case, x belong to the n. Okay, I can say z such that the x belong to 0 and 1. How many elements of this set? If x belong to the z. Please give me the answer. Hello, friends. You also can give. How many elements of this set? You see here, x derives from 0 to 1. 2, correct. Which one? 0 and 1. Okay, if I take tail, not z, n, such that x belong to 0, 1. What about this set element? How many elements? Now x belong to the n. When x belong to the z, it has only two numbers, 0 and 1. It is finite according to that definition. So we can, for this case, how many elements? If x belong to the n and x belong to the 0, 1, so how many elements here? How come infinite? Yeah, it's only natural number from this set, 0, 1. 0 is not natural number. Only 1. Only 1. Now, please pay attention. Even one set, if I put the condition, then this set becomes finite set. Okay? This set becomes only one element. This set it becomes only. But what about Q? How many Q there? Can I state here? Okay. What about here? From 0, 1. So x belongs to the Q. So 0, 0.1, 0.2, 0.9, and 1. That's all, or we have some more? Rational. Only 10? 1, 2, 3, 4, and 10. 11. No more? Okay. Yep, it should be between 0, 1. Next, 0.01 is also a rational number. 0.02 is also 0.0 129. Yes, you can write down. You cannot stop. You cannot stop the element of the Q in the interval 0, 1. You see? Just now you have seen. For n, we have only one element. For the z, we have two elements only. But when we come to the Q, we have infinitely many elements. But interesting point, this one, I can make equivalence with n. Equivalence with n. But if I consider sets like this, then I cannot. Look, here I'm writing this set as, you see, this is the largest set. This is a set of x from R such that x belongs to 0, 1. Now this one I cannot count by n. Okay, so we are coming to that point actually. Okay, so you see, the rational number set is a countable set. The rational number set is countable set, but n r is not countable set. We cannot find bijection function such that all the values. See, this is very small interval 0, 1, but it has so many interesting properties. And from this interval, we can make any type of conclusion. Okay, so that's why this general scheme is like that. Now I will go through it. Okay, what are they going to say? How to prove that this set is countable? I mean, it is a denumerable set. And this one is not equivalent set. There is no equivalent set between. It is not denumerable. It is not finite. Okay, and as well. Okay, so now let us go through. Already what time? Maybe just little 5 minutes rest. Okay, because how to prove? You concentrate. Okay, so exam, what day? Tuesday, what time? 1.5 hours. 1.5 hours. So from 2 to 3:30. Okay. So I already constructed the paper. I mean the quiz 2. As I told you, all from the chapter 2 and only first part. Okay. Not equivalent sets, not including discountable sets, is not there. So, any other suggestion, questions, you are welcome. So I can make a little bit bigger.
Doctor, does the question have proof? It's a proof something?
The quiz.
Yes. All three is proof. One example.
Is a quiz. But this example, this problem is just I give the function to lead to calculation. For example, the A set is given. Find f of A, for example. Okay. According to the definition, you need to just count it and find it. The first example is very simple. Just example. Second one, I construct such a way that we need to prove. Okay. Using the, for example, some theorem above.
theorems. But you have to put for the by theorem 2.1 get this, theorem 2 to get this, so we will complete like this. But we need to probably for the injectivity you have to prove it by definition f of x1 equal to f of x2 implies x1 x2. Okay, if h is injective, how to show, for example, f minus 1 is also injective. Okay, so because of this properties should show that f minus 1 at point y1 y2 equal to y1 equal to y. Have to prove. So the second one is with some kind of function, but we need to prove. Okay, and most of them is only from the first part of the chapter. Okay. Yes.
Doctor, you want to go to toilet first?
Okay.
Doctor, we have to send by email or email? The email. Ada sampai yang ya. Kenapa Pak? Tuh ya aku dengar sepi ya. Aku yang cemot tak jadi. Foto.
So, I to finish.
Okay, let me continue. So next, please again, a non-empty set S is called finite if there is a bijection function of S with the set of form. That's the best definition. For some positive integer n. If no such bijection function exists, then the set is called infinite. So a set S is denumerable if A is equivalent to n. Okay, and it is countable. A set is called countable if it is either denumerable or finite. Okay, so using this definition, now we will prove the following: that every subset of n is countable. Every subset of n is countable. So how to prove? So it is called lemma. Lemma. Every subset of n is countable. Every subset of n is countable. Please pay attention. What does it mean, countable? A set is called countable if it is denumerable or finite. Finite. For the finite, for the finiteness, so if any set is equivalent with 1, 2, and n. For the denumerable, we have the equivalentness of A with natural number set n. Okay? In both cases, it is called countable. If it is finite, it is countable. If it is infinite, then it is still countable. Infinite, but equivalent with the n. So it is called. Okay, now every subset of n is countable. How to prove? Proof. Proof. Suppose S is a subset n. This is okay. This is correct. Suppose some set is subset of n. Proper subset or subset. Look, if I put this one, we call it subset. If I remove this one, it is called proper subset. There is a difference between them. So it is a subset of n. So if S is finite, then it is countable. It is correct. The first part, if S is finite, then it is countable. If S is finite, then it is countable. Because if set is finite, it is countable. That's very, very clear. So now by definition, if S is an infinite, then it is not empty. Okay. So second part, if S is infinite, then it is not empty. It is correct. It is not empty. It is not empty. Correct. It is infinitely many elements. It is not empty. So now from that point we will start. If it is not empty, and by the well-ordering principle of n, S has a minimal element. Okay, it is not empty. It has minimal element. Minimum. Yes, it's correct because minimal element n1. Imagine S has infinitely many elements, but because of well-ordering principle of n, it must have some minimal element. Right? That element will be denoted by n. Then we take out from S, we take out this number n1. So it means we reduce one element. So the next set, let's say this one is S1. I take out. So this S1 has, because of well-ordered principle of n, this set is also not non-empty, and it has minimum element n2. So we have the minimum element n2. If so look, if from S I take out these two minimal elements, so this S2 still has infinitely many elements. Right? Just we take out two elements. From infinite elements, we take out two, still it has infinitely many elements. So from the above proposal or suggestion, this S2 is also not empty. It's not empty set. And it has minimum element. So by this type of minimum element taking out, I will construct the T sets consisting of N1, N2, and N3, and so on, actually. See? Imagine one element take out, we have infinity element take out. Take out two, also we have three, we have. Right? If we take out 1, 2, 3, 4, not finite, infinity element. This consists of T set. Every time CS1, this T, the first minimum element of the S, M2 is a minimum element of the second S, S2, S3, S4, and so on. You see, every time we are taking out, and constructing the new, what we call it, the set, new set. All the minimum element of S. But you can see it is infinitely many elements. Okay, so we can counting in this manner, we form the set where NK actually here can be written as minimum of S minus N1, N2, and A can minus 1. N1, N2, and Nk minus 1. Look. So NK is correct. So every time this is the finite element. So because NK is when we take out the NK minus 1 elements from S, then minimum of this set is NK. When K equal to 1, we have this set. K equal to have this set, and so on. It is okay. Everything is correct. So now we note that, but here, because of well-ordering principle of N, so N1 should be less than N2. N2 should be less than N3. It is also correct because, you know, the N1 is the first element from the S, minimum element. N2, after taking out the N1, we have the N as element, and minimum element of N2 from this set. So it is greater than N1. So it is well ordering. Note that this one is correct. Then function. So, and here we have the function. And function f, mapping from n to t is given by this f of k equal to n sub k. Okay, now you see we are able to construct bijection function. This one is nk. It looks like x. You know, x is a bijection function. So here it is you see f of k is equal to nk. We are able to construct the function, and this function is a bijective function. If it is bijective function, then S, if it is bijective function, then S, actually our aim is to countable. It is countable, because the S is equivalent to N. If we are able to show that this function is a bijective function, then S is equivalent to N. If equivalent to N, so when S is infinite cases, also it is countable. This one shows that it is countable. How they are showing here, you can see that after this, clearly it is bijective, and thus this T, actually not S, this T, sorry, because NK depend on the T. The T is equivalent to N. So to complete the proof, we shall show that T equal to S. Okay. Actually, after this, if we show that this one is a bijective, then T is equivalent to N. Equivalent N. To be equivalent, T is what actually? T, we are constructing such a way that minimum element from the first set, second element. So actually, we are taking out all the elements of S. So it means actually this N1, N2, N3 taken out from the S, but after infinitely many elements, this T actually becomes equal to S. Equal to S. And since T is equivalent with the N, so from here I can say S from equivalent to N. Because of transitivity. If A transitive to B, then B transitive to A. So you see, T is a transitive N, and the S must be transitive equivalent to N. Okay? So actually over there says like this. First of all, T is a subset of S. It is clear because we are constructing T by taking out N1, N2, and etc. So it is a subset of S.
Now, to be equal, so this one is, it is since T is a subset of S. Now, we have to show S is a subset of T. Okay, S is a subset of T. So it means every element of S is an element of T. We need to show. So that the last one is stated over there. See, since N1 and like this. Can you little bit down? Okay, stop. Okay. I hope over there already clearly stated, because time is not much time. We have to look. T is a subset of S is clear because of construction. On the other hand, now how to show this? It is known N1, N2, and N3 as ordering. So and K, actually K is also less than the K is less than NK. Okay, this one also can understand. Because K equal to 1 is N1. N1 is not equal to 1. It might be 2, 3, whatever. So that's why K, this equality always holds. Okay? So second step, the K, less than for all K from N. This is correct. Next, we suppose that now we are taking element M from S. Okay, we are taking any element from S. Okay, and S is a subset of N. It is clear because N is a large subset. Large set because S is a subset. So after that, what we can say, we know that well-ordering property that the non-empty subset has a minimal element, and by definition, M equal to Nj. So now this element M, actually there is a J. So this M is equal to 1 of Nj. There is no other case. So if N equal to Nj, Nj is the element of T. So from here, I can say M is belong to T as well. But this M is any element from S implies M is element of T. Okay, here the ordering property of the what you call it, ordering property of integer number, okay, is important. So K is less than NK, and if we take any M from S, so it will be element of T. There exists T such that N equal to NG, one of the NG. So generally, imagine the proof comes like this. From S, we take out 1 element, 2 element, 3 element, infinitely many elements. It looks like S getting smaller, and become empty actually. Becoming empty. But it is still not empty. So this taking out and constructing the new T, actually approaching to the S. Then for large NK, actually they are coincide with each other. But T, you see, because of construction, here important one, this function is bijective function. Bijectivity implies T is equivalent to N. And on the other hand, T equal to S. Okay? So if we prove T equal to S,
and n is equivalent to n, you can calculate s equivalent to n. So it is countable. Countability is not very simple, but it is proven like this. Okay, the last one. The next is what? Every subset of countable set is countable. Previously, what we proved, every subset of n is countable. Now, this one a little bit now generalization. Actually, every subset of n is countable because of natural number. So now we can generalize this one. Every subset of countable set is countable. Okay, and I hope this proof I will skip for you. See, generally it depends on the inverse function and action and so on. Can you go to the next? So if set A and B both countable, then A times B is countable. Okay, can you scroll down? Because this one is also okay, but for me, I am going to prove the original number set. Okay. Okay, a little bit up. Let me see that. Okay. Up. No, down. Just okay. Okay. So, what does it mean? A times B. It is a Cartesian product. Huh? See, if A and B are both countable, then that Cartesian product is also countable. So, proof. First, assume that both A and B are infinite. Actually, if it is finite, we can easily can get. Actually, what does it mean? For example, if set A is countable, let's say n1, n2, and nk, and B is has another set m1, m2, and etc. m l. If it is countable, the finite, it's what we call it finite. Then the product, this product, is, if you remember, it is a set of, n1, m1, n1, m2, and etc. n1, ml. Then second, n2, m1, n2, n2, and etc. Okay, so n2, ml, and etc. Actually, we have finite nk, m1, nk, m2, and etc. So generally, this one is countable. Nothing problem in ml. Okay, if it is finite, then it is countable. Very clear. When it is infinite, then still can be counted. Yes, can be counted. How to prove? Actually, you see, here they define the function in the form of the new function, you see, and but this one is not easy actually, but it is already stated there. You see, for the infinite, we need to find bijective function. Okay, for the infinite set, we need to find bijection function. Just now, we have found f k equal to nk. Nk was minimum of set S subtracting n1, n2, and nk minus 1. Look. Okay, we are constructed function like this. For this case, they construct like this. By define it now. F mapping n, mapping A to n, and G mapping B to n also. to n. N is a natural number set. So then we have two bijection functions. Define the function like you see. Okay, a the function f mapping a to n. If the set is both countable, if countable, yes. If even it is enumerable, so the a, the function f mapping a set to the n, set b mapping to the n, because of uh, the bijective. Then we have two bijective functions. So two bijective functions. Both countable, then this one. Okay, now define the h function. H function. A, B, that we called the product, Cartesian product, mapping to n, is defined by these. How they able to find, this is another issue, but currently we just f of x, then 3 g f of y, g of y, Okay, now this is exponential function. So this exponential function, what time is it? 56. Now we have another few minutes. Okay. Now by the theorem 3.3 and remark 3.1 in chapter 1, f of x1. So actually, they are showing that first they are what we call it injective. Actually, I think injectivity very clear because 2.f of x1, 2.f of xt, if so, f1 equal to f x2 and g x y1 is g y equal to that it is correct, and since f and g are bijective and f is a bijective, g is a bijective, that's why this equality implies that, and since f and g are bijective, this implies x1 equal to x2, y1 equal to, thus h is bijective and defined like this. Actually, proof, you see, after constructing this, we need to show this function is a bijective. For the bijectivity, first we need to show it is injective. Injective means so x1 y1 h of x1 y1 equal to h x2 y2 implies we have to show this x1 equal to x2 and y1 equal to y2. But only here f and g are bijective. So because of bijectivity, we can get that one. Okay, so that's the proof of this. And just how to explain these two important theorem I am leaving for you. Maybe tomorrow I repeat the important. This one are very important. If A is a countable set for every n, then this one is also countable set. Okay, this one also we can prove, but this one is important. The set of rational numbers is denumerable. Okay, tomorrow I will show you why this one is denumerable. Why the set of real numbers is not denumerable. Okay, these two theorems I will prove. This one, I think you can learn it yourself. Okay, because if countable set, then but this union is infinite union. Still, it is countable. This theorem is countable. Then Cartesian product is also countable. Okay, So these two tricks you learn yourself. So I will prove tomorrow if rational number is the set of rational numbers is denominator, and the set of real numbers is not denominator. Okay. So this one I will prove tomorrow. Okay. So you see, generally it is looks like easy, but still not easy, right? And for exam, please be ready. So I almost told you where is it. So please read it, exercise it, read. But you see, this lecture notes has not many exercises actually. So I have to top up the exercise. Okay, thank you very much. If no questions, that's all. And please attend that. I don't have, I to get another time to see. So Tuesday, every student must come. Okay, online. Thank you very much for coming and helping. Okay, good students. Okay, thank you very much. So in the case I'm going to finish. That's all for today. Enough. Thanks.